Now we're going to take a look at this motion here as we consider this object that has an angular speed and over a period of time. And we notice here the angular speed starts at time equals 0. It starts at 12 and then eventually gets down to 0. So what I'm going to have you try is practice this one to find the angular acceleration of the mass, and then also to find the angular displacement of the mass. And so there's actually different ways to do that, and you can go ahead and try this. So go ahead and pause the clip and see if you can get that, and then when you're ready to check, you can hit play to continue. Okay, so we know the angular acceleration is the change in omega, the change in the angular speed over a period of time. So the final, angular speed minus the initial angular speed over time. We should get -3 radians per second squared as the angular acceleration. And then once we have that, we can solve for, the angular displacement of the mass. You could use one of the kinematic equations that you have, or if you notice here, right, omega is on the omega is on the y-axis, the time is on the x, and so those two things are being multiplied. So it turns out that the area here represents the displacement, in this case 24 radians. The other way to do that would be use one of those 4 constant acceleration equations that we used in a previous lesson to figure out how far it goes. And so you could have used either one there. Okay, so if I take a wheel and axle, and let's say the axis of rotation is right here, and I push on this, I can make it go translationally. I can make it move like that. But if I push at the top, I can actually cause this to rotate around, right? And so that's what we're going to look at now, is how force can enact a rotation and explore that. So let's make the middle of the axis of rotation here. You can draw that. Let's say that the surface is frictionless. If I push straight on to this mass, it'll slide, and so it'll have translational motion. But if I apply a force at the top, I can get a different effect here. So, if this is my lever arm right here, and this is my force, I can figure out how much torque, and therefore it'll rotate. So let's say that we have a force of 30 newtons. The lever arm is 0.2 meters, and we want to figure out how much torque this will cause. So pretty straightforward there. In this case, will be -6 Newton meters of torque, or clockwise torque, as it goes around. And yeah, so this is nothing new. We just practice from the torque section. Now, let's say we look at this situation where we push through kind of in between the middle there and the top. Well, we know we're not going to get as much torque. The lever arm is less, and we're applying that force not perfectly where it needs to be. So what we're going to do is we draw this line from the middle. This is this green line, and we see where that intersects. We draw that to where it intersects the line where the force is coming through here. So those two meet. So let's say that this angle right here is 28 degrees, which makes this also 28 degrees. What this means is only a portion of this force is actually going to count for torque. And so the only portion that's actually going to count up as part of this force is this part of the force. Because, this force right here is right here. We can break that up into this component and this component. So this plus this equals the hypotenuse. And so, let's say that let's say we have 18 newtons of force here, and the angle is 28 degrees right here. The only amount of force that's going to count is this 8.45 newtons of force. Sine equals opposite over hypotenuse is a right triangle. Right, so if this angle right here is 28 degrees, the opposite side is this, the hypotenuse was this. So therefore, it's kind of like this. It's like having a radius of 0.4, only this length right here, times this force to make it rotate. And it'll rotate around like that, which if we look back at this original picture, it's going to make it rotate, rotate around. And really, this force right here is this, which is the only the component that we found out from this one. We can also, and then we can calculate the torque. So we have the force, we have the displacement in meters. So negative 0.338 Newton meters. The other way to look at this is to look at the lever arm. So in other words, as we push this, the torque here will be caused over this lever arm length. And so we could break this up to find how long that is. And in this case, if the radius is 0.4 right here, this portion of that radius, if we look at, this is this line right here is this. This is a right angle. So this angle right here that we have, coming in is the same as that we used before, the 28 degrees. And so we could find that length, and we'll end up getting the same thing, negative 0.338 Newton meters. Okay, at this point, we can take a look at an object that has a different kind of shape. Let's say something like this, where the axis of rotation is here. And so as this spins around, it's got an irregular shape, and the motion of it's going to be a little bit strange. So let's take a look at that in terms of torque on an object like that. Now, let's say this is the axis of rotation right here. If we apply force, let's say we push on here, and this is the axis of rotation. It's like pushing on a hinge. We can, we're just going to make it go that way. Or if we push this way, right, and just straight through, it's going to go like that. As compared to if we pushed, let's say we pushed over here, we can make this rotate. This is an axis of rotation for this object. So let's take a look at this example here where we have a force of 20 newtons exerted on a disc. The force is at a 25-degree angle to the axis, and it's a distance of 0.3 meters. So we want to find out the torque on the object. So this is very similar to what we did before. We're going to have to break down what the force is here and see which portion will actually make the torque happen. Or again, we could break up what's going on there. So let's say we can use this using the short lever arm here. Let's say we have 20 newtons of force, and let's say the angle, or the D right here is 0.127 meters. We can get the torque pretty easily. This would be negative 2.54 Newton meters. This will be a clockwise torque. Now, if we use the radius, like the full length here, right, and we need to break up the force, we can do that as well. The only force that's going to count is this opposite side right here. So we break down this force into this component and then this component, and this is the only component here that's going to work. So that portion of the force is 8.45 newtons, and which is in red there. And then that's over that radius there,